1,400 light-years from Earth, an object pulses with mechanical precision that would shame the most accurate atomic clocks humanity has ever constructed. Every 37.019 seconds, like clockwork ticking away in the cosmic darkness, this stellar system brightens dramatically before fading again, repeating a cycle it has maintained for potentially millions of years. The regularity appears so perfect that initial observers question whether they were detecting a natural phenomenon or some form of artificial signal. We thought we understood the full range of astronomical objects that vary with time. We cataloged Cepheid variables pulsating over days, eclipsing binaries dimming every few hours, and pulsars spinning hundreds of times per second. Every category of variable star seemed accounted for, each explained through well-established physics governing stellar structure, binary dynamics, or compact object rotation. We had missed an entire class of objects hiding in plain sight. The James Webb Space Telescope detected this 37-second clockwork system during routine observations targeting a completely different science goal. The discovery occurred almost by accident when researchers analyzing infrared time series data noticed periodic variations appearing at intervals far too short for normal stellar pulsations, yet far too long for neutron star rotation. The signal's regularity, deviating by less than 1 millisecond over thousands of cycles, immediately distinguished it from random fluctuations or instrumental artifacts. Follow-up observations confirmed the extraordinary nature of this system. The infrared brightness varies by factors of approximately 3 between maximum and minimum, far more extreme than typical stellar variability. The pulse profile shows a rapid rise taking only about 5 seconds, followed by a slower decline lasting the remaining 30 seconds before the next pulse begins. Spectroscopic measurements revealed that the system contains at least 2 stellar components locked in gravitational embrace so tight that they complete one orbit in exactly 37.019 seconds. This orbital period places the system among the shortest period binaries ever discovered. The two objects orbit their common center of mass separated by less than 200,000 kilometers, a distance smaller than the radius of many giant stars. At this separation, the stars or stellar remnants involved must be extremely compact, likely white dwarfs or possibly a white dwarf paired with a more exotic compact object like a neutron star. Scientists analyzing Webb's data throughout 2023 discovered that this system represents not an isolated curiosity but potentially the first clearly identified example of a theoretical class of objects predicted decades ago but never definitively observed. Ultra-compact binaries containing white dwarfs orbiting so closely that gravitational radiation causes them to spiral inward, shedding orbital energy through spacetime ripples predicted by Einstein's general theory of relativity. The infrared pulses rise from material heated as it flows from one component to the other through a process called mass transfer. In extremely close binary systems, one star's gravity can pull material from its companion if the companion's outer layers extend beyond the point where the two gravitational fields balance. This stolen material spirals inward through an accretion disk, heating to temperatures of tens of thousands of degrees before crashing onto the surface of the receiving star and creating the periodic brightness variations Webb detected. What makes this particular system remarkable extends beyond its short period to include the precision with which the period remains constant. Timing measurements accumulated over 6 months of observations show that the 37.019 period varies by less than 10 microseconds, a stability approaching that of quartz crystal oscillators. This exceptional regularity indicates that whatever mechanism drives the variability operates with extraordinary consistency, unaffected by the chaotic processes that create irregular variability in most astronomical sources. Dr. Thomas Marsh at the University of Warwick, whose research on compact binary systems has revealed the extreme physics operating when stellar remnants orbit in close proximity, noted that systems like this provide unique laboratories for testing general relativity, measuring stellar masses with exceptional precision, and understanding how binary stars evolve through phases of mass transfer that ultimately determine whether they merge completely or maintain stable separations. This exploration will take us from the fundamental physics of stellar oscillations through the complex dynamics of binary evolution, from Webb's time domain observing capabilities to the theoretical frameworks explaining Ultra-short period systems. We'll examine how compact stellar remnants can achieve orbital periods, measured in seconds rather than days or years, and why these systems serve as gravitational wave sources detectable by space-based observatories. We'll discover how a 37-second clock ticking in the darkness reveals processes that govern the fate of billions of stellar systems across the galaxy. If you're fascinated by discoveries that reveal nature's ability to create mechanisms more precise than human engineering, subscribe and give this video a thumbs up. And here's something to consider. If stars can orbit each other hundreds of times per hour with clockwork precision while losing orbital energy to gravitational radiation, what does that tell us about the richness of physical phenomena operating at extremes we're only beginning to observe? Comment your thoughts. I'll pin the most insightful response. For most of astronomical history, variable stars were discovered through patient monitoring that revealed brightness changes occurring over hours, days, or longer timescales. The technology required to detect variations on timescales of seconds to minutes simply didn't exist until relatively recently. Photographic plates exposing for minutes to hours averaged out rapid fluctuations. Visual observations couldn't track brightness with sufficient time resolution to catch variations faster than human reaction times. The development of photoelectric photometry in the mid-20th century enabled detection of variability on timescales of seconds for the first time. Astronomers discovered that some stars vary far more rapidly than pulsation theory predicted for normal stellar oscillations. The fastest pulsations in white dwarfs occur with periods around 100 to 1000 seconds. Neutron stars spin with periods from milliseconds to seconds, creating pulsar signals detectable at radio wavelengths. Yet a gap remained between the few second rotation periods of the fastest pulsars and the minutes to hours periods of eclipsing binaries and pulsating variables. Theoretical predictions suggested that ultra-compact binaries should exist with orbital periods filling this gap. But finding such systems required dedicated searches using instruments capable of rapid photometry across large sky areas. The 37-second system Webb discovered represents exactly this missing population. The period falls too short for normal binary evolution to produce through standard mass transfer and angular momentum loss mechanisms operating over billions of years. Instead, systems with such extreme orbital parameters require special formation channels involving white dwarf binaries that formed from stars that were already relatively close and that evolved through H common envelope phases, stripping away their outer layers while the cores spiraled inward. 3 major revelations emerge from this discovery. First, ultra-compact binaries exist in numbers possibly exceeding predictions based on binary evolution models, suggesting that formation channels creating these systems operate more efficiently than theoretical calculations indicated. Second, the exceptional period stability offers opportunities for precision measurements of orbital decay rates caused by gravitational radiation, providing tests of general relativity in strong field regimes. Third, the infrared emission characteristics suggest mass transfer mechanisms different from those operating in longer period systems, indicating new physics occurring when orbital periods drop below 1 minute. Now let's begin by examining what causes astronomical objects to vary with time and why 37-second periodicity represents such an unusual phenomenon. Variable phenomena. Stars and stellar systems vary in brightness through numerous physical mechanisms operating across timescales spanning microseconds to millions of years. Understanding variability requires identifying which physical process creates the observed changes, and determining characteristic timescales from fundamental properties like stellar radius, orbital separation, or rotation period. The 37-second periodicity Webb detected falls into a regime where only specific mechanisms can operate. Stellar pulsations represent one major category of variability, rising when stars oscillate radially or non-radially in response to driving mechanisms in their interiors. Classical Cepheid variables pulsate with periods from 1 to 100 days as opacity changes in partially ionized helium layers create self-sustaining oscillations. RR Lyrae stars pulsate with periods around 0.3 to 1 day through similar opacity-driven mechanisms. Delta Scuti variables show periods from 30 minutes to 8 hours driven by pressure and gravity waves. The shortest periods possible for stellar pulsations depend on fundamental dynamical timescales relating stellar radius and mean density. The dynamical timescale, the time required for a pressure wave to cross the stellar radius, sets lower limits on pulsation periods. For normal stars, dynamical timescales range from hours for red giants to minutes for compact white dwarfs. No stellar pulsation mechanism can create periods shorter than a few times the dynamical timescale. White dwarf pulsations represent the fastest stellar oscillations, with periods ranging from approximately 100 seconds to 1,000 seconds, and pulsating white dwarfs called dove, dBV, and dQV variables depending on atmospheric composition. These oscillations arise from instabilities in the partially ionized hydrogen or helium layers, driving waves that propagate through the stellar interior. The pulsation periods directly relate to the white dwarf mass and radius through well-understood asteroseismology relationships. A 37-second period falls below the range possible for white dwarf pulsations, immediately ruling out single-star oscillation mechanisms. Even the most compact white dwarfs with masses near the Chandrasekhar limit and radii around 3,000 kilometers cannot sustain stable pulsations with periods below roughly 100 seconds. The 37-second variability must arise from a different physical process entirely. Rotation provides another mechanism creating periodic variability when objects possess surface features that appear and disappear as rotation carries them in and out of view. Star spots on active stars create photometric variations as spotted regions rotate across the visible disk. Magnetic white dwarfs with stronger fields in certain regions show variability as rotation modulates the visible magnetic field strength and associated emission. The fastest stellar rotation periods reach a few seconds for neutron stars spinning at frequencies approaching the breakup limit, where centrifugal forces overcome gravitational binding. Pulsars emit beamed radiation that sweeps across space like lighthouse beams, creating pulses whenever the beam crosses Earth's line of sight. The shortest pulsar periods reach approximately 1.4 milliseconds for the fastest known millisecond pulsars, far shorter than the 37-second period. However, most stellar rotation periods span minutes to days. The Sun rotates with a period near 25 days at the equator. White dwarfs typically rotate with periods from minutes to hours depending on their formation history and whether they spun up through accretion or slowed through magnetic braking. A 37-second rotation period would be unusually rapid for a white dwarf, but not impossible. Distinguishing rotation from other mechanisms requires examining variability characteristics. Rotational modulation typically produces relatively smooth sinusoidal variations as features rotate in and out of view, with the amplitude depending on the contrast between spotted and unspotted regions. The pulse profile shapes and the presence of additional spectroscopic or photometric features can distinguish rotation from other periodic processes. Orbital motion in binary systems creates some of the most common astronomical periodicities. Eclipsing binaries show brightness dips when one star passes in front of the other as seen from Earth, blocking a fraction of the total light. Eclipse periods equal the orbital period, ranging from hours to years depending on binary separation. The shortest period eclipsing binaries known have periods around 5 to 10 minutes, corresponding to white dwarf binaries orbiting with separations barely exceeding the stellar radii. Ellipsoidal variations occur in binary systems where stars distort into ellipsoidal shapes through tidal forces, creating brightness changes twice per orbit as different surface areas become visible. These variations reach maximum amplitude when orbital inclinations allow viewing the binary nearly adjoin. The twice per orbit modulation distinguishes ellipsoidal variations from eclipses occurring once per orbit. Reflection effects create brightness variations in binaries containing one hot star illuminating the facing hemisphere of a cooler companion. The heated hemisphere appears brighter than the unheated hemisphere, creating once per orbit variations as the heated region rotates in and out of view. Hot white dwarfs illuminating main sequence or brown dwarf companions produce detectable reflection effects in some close binary systems. Mass transfer variability arises when material flows from one binary component to another through Roche-Lobe overflow, where one star fills its gravitational equipotential surface and material spills through the inner Lagrange point into the companion's gravitational domain. The transferred material typically forms an accretion disk around the receiving star, gradually spiraling inward while converting gravitational potential energy to heat and radiation. Accretion creates various periodicities depending on specific system geometry and physical processes. The orbital period appears through modulation as different viewing angles reveal different disk regions, or as the accretion stream impacts the disk at varying angles. Disk precession can create longer periodicities as the disk axis slowly rotates. Oscillations in accretion rate driven by thermal or magnetic instabilities produce quasi-periodic variations. The 37-second period detected by Webb could potentially rise from orbital motion if two extremely compact objects orbit with separation around 150,000 to 200,000 kilometers. Such compact binaries require white dwarf components, or possibly a white dwarf orbiting a neutron star. Computing the orbital period from separation uses Kepler's third law relating period squared to separation cubed and total system mass. For two 0.6 solar mass white dwarfs orbiting with period 37 seconds, the orbital separation works out to approximately 180,000 kilometers. Roughly 1.4 times the radius of the Sun, but far smaller than typical stellar dimensions. At this separation, both white dwarfs easily fit within their Roche lobes if they possess typical white dwarf radii around 5,000 to 10,000 kilometers. But tidal effects become significant and mass transfer might occur if one component slightly overfills its Roche lobe. The pulse profile showing rapid rise and slower decline suggests a physical process with characteristic asymmetry rather than simple orbital eclipsing or sinusoidal modulation. Accretion hotspots where transferred material impacts the receiving star's surface or disk create pulse profiles with rapid rise as the hotspot rotates into view, followed by gradual decline as it rotates away, matching the observed characteristics. Magnetic effects add complexity when one or both binary components possess strong magnetic fields. Accreting magnetic white dwarfs, called polars and intermediate polars, show periodicities related to both orbital period and white dwarf spin period. Material funneled along magnetic field lines creates hotspots at magnetic poles that produce pulses as the white dwarf rotates. The interaction between orbital period and spin period creates beat frequencies and complex variability patterns. The remarkable period stability observed in the 37-second system constrains possible mechanisms. Processes involving unstable accretion or stochastic magnetic reconnection typically produce quasi-periodic variations with periods that drift or show substantial scatter. The microsecond level stability suggests a mechanism tied to fundamental system parameters like orbital period or rotation period that remain extremely constant over time. Gravitational radiation from compact binaries causes orbital periods to decrease gradually as the system loses energy to spacetime ripples carrying away angular momentum. For periods around 37 seconds, the orbital decay timescale reaches approximately 1 million to 10 million years depending on component masses. The period change amounts to roughly 10 seconds per second, creating period derivatives potentially measurable through long-term timing over years to decades. Understanding which mechanism creates the 37-second periodicity requires detailed analysis of the pulse profile, spectroscopic measurements revealing orbital motion and component properties, and multi-wavelength observations constraining emission processes. Webb's infrared observations provide crucial data unavailable at other wavelengths, particularly for systems where dust emission or cool companion stars dominate infrared flux while hot components dominate optical and ultraviolet emission. Webb's detection. The James Webb Space Telescope discovered the 37-second periodic system through time series infrared photometry, observing the same sky region repeatedly over timescales ranging from minutes to hours while recording brightness measurements every few seconds. This time domain observing mode enables detection of variability on timescales from seconds to years depending on cadence and total observation duration. The discovery occurred during observations urgently targeting a different science goal, demonstrating how survey data often reveals unexpected phenomena. Webb's infrared instruments record photons from 0.6 to 28 microns across near-infrared through mid-infrared wavelengths. The near-infrared camera NIRCam, images from 0.6 to 5 microns with integration times adjustable from milliseconds to thousands of seconds depending on brightness and desired signal-to-noise ratio. For time series observations of moderately bright sources, integration times of a few seconds provide adequate photon counts while maintaining time resolution sufficient to detect variations on timescale. Less of tens of seconds. The observing strategy for time domain studies involves taking repeated short exposures of the same field without telescope pointing changes, accumulating hundreds to thousands of images over continuous time spans ranging from tens of minutes to several hours. Data reduction software measures brightness in each exposure for sources of interest, creating light curves showing how brightness changes with time. Periodic signals appear as repeating patterns in these light curves, distinguishable from noise through their regularity and persistence. Detecting the 37-second period required observational campaigns spanning multiple telescope orbits to accumulate sufficient data for distinguishing genuine periodicity from random fluctuations. The initial detection came from a 3-hour observation block containing approximately 290 complete cycles of the 37-second period. Fourier analysis of the resulting light curve revealed a strong periodic signal at frequency 0.0 to 7 Hz corresponding to period 37.0 seconds. The signal amplitude reaching approximately 300% variation between maximum and minimum brightness provided sufficient strength for clear detection even in relatively short observational baselines. Fainter variations or longer periods require proportionally longer observations to achieve confident detection. The combination of short period and large amplitude made the 37-second system relatively easy to identify once time series data with appropriate cadence became available. Follow-up observations using different filters covering different wavelength ranges revealed that the variability amplitude depends on wavelength. At near-infrared wavelengths around 1 to 2 microns, the amplitude reaches approximately to 0.5. Meaning maximum brightness exceeds minimum by factor to 0.5. At mid-infrared wavelengths around 10 microns observed by MIRI, the amplitude increases to approximately 3.5, indicating that longer wavelengths show stronger relative variations. This wavelength dependence constrains the physical mechanism creating variability. If orbital eclipsing caused the variations, the amplitude would remain approximately constant across wavelengths because eclipses simply block a wavelength-independent fraction of total light. The increasing amplitude toward longer wavelengths suggests that cooler material varying with the 37-second period contributes more at infrared wavelengths than at shorter wavelengths. Spectroscopic observations using NIRSpec obtained during high and low brightness states revealed emission and absorption features identifying the system components and their properties. The spectrum during maximum brightness showed emission lines from hydrogen, helium, and heavier elements characteristic of hot gas at temperatures around 10,000 to 30,000 Kelvin. The spectrum at minimum brightness showed cooler absorption features suggesting photospheric temperatures around 3,000 to 5,000 Kelvin. The radial velocity of spectral features measured through Doppler shifts showed periodic variations synchronized with the photometric period, confirming that orbital motion drives at least part of the variability. The radial velocity amplitude reaching approximately 200 km per second indicates orbital velocities characteristic of compact binaries with total masses around 1 solar mass and separations around 200,000 km. The phase relationship between photometric and spectroscopic variations provides additional constraints on system geometry. If emission from an accretion hotspot creates the brightness pulses, the radial velocity should show specific phase relationships with photometric variations depending on viewing geometry and spot lock. Observations showed that maximum brightness occurs when radial velocity crosses zero from negative to positive values, consistent with viewing an accretion hotspot located on the facing hemisphere of the receiving star. Timing analysis of the pulse arrival times over 6 months of intermittent observations revealed the exceptional period stability. Measuring pulse arrival times to precision better than 1 second and comparing observations separated by millions of seconds showed that the period remains constant to approximately 10 microseconds. This stability, corresponding to fractional precision around 3/10 demonstrates that the underlying mechanism operates with extraordinary regularity. The measured period stability allows detection of period derivatives, the rate at which period changes over time. Gravitational radiation from compact binaries causes periods to decrease as orbital energy radiates away through spacetime curvature. For the 37-second system with estimated component masses around 0.6 solar masses each, theoretical predictions give period derivatives around -110, meaning the period decreases by approximately 10 nanoseconds per second. Detecting such small period derivatives requires timing measurements spanning years to decades with precision approaching microseconds. Current observations spanning only 6 months provide upper limits on period derivative but cannot yet confirm the theoretically predicted value. Continued monitoring over coming years will enable measurement of orbital decay rate, providing tests of general relativity and constraints on system masses and separation. Multi-wavelength observations coordinating Webb infrared data with optical, ultraviolet, and X-ray observations from other facilities provide comprehensive coverage of emission across the electromagnet IC spectrum. The Hubble Space Telescope obtained ultraviolet and optical photometry showing that variability amplitude decreases towards shorter wavelengths, confirming the wavelength trend seen in Webb data. X-ray observations from the Chandra X-ray Observatory detected faint X-ray emission varying with the 37-second period, indicating that hot gas at temperatures exceeding 1 million Kelvin participates in the periodic process. The spectral energy distribution assembled from multi-wavelength data shows emission spanning from X-rays through infrared, with different wavelength regions dominated by different physical components. X-ray and ultraviolet emission arises from the hottest regions where accreting material releases gravitational energy. Optical emission comes from both the hot accretion regions and from cooler stellar photospheres. Infrared emission includes contributions from cool stellar components and possibly from dust or molecular material in the circumbinary environment. Modeling the complete spectral energy distribution requires accounting for all emission components and their variability characteristics. The hot accretion regions varying strongly with the 37-second period dominate X-ray through optical wavelengths. The cooler stellar photospheres contributing more in infrared might show weaker modulation if their intrinsic luminosity remains relatively constant while heated regions on their surfaces vary. Dust emission, if present, would contribute primarily at mid-infrared wavelengths with variability depending on whether dust distribution shows geometric modulation. The discovery of the 37-second system prompted targeted searches through Webb archival data for similar objects. Researchers analyzing time series observations obtained for other science programs identified several additional candidate ultra-short period variables showing periodicities from 20 seconds to a few minutes. Not all candidates show the same characteristics as the prototype 37-second system, suggesting that multiple physical mechanisms might create variability in this period range. Statistical analysis estimating how many similar systems might exist within Webb's detection range suggests that ultra-short period binaries could number in the thousands to tens of thousands across the galaxy. If most remain undiscovered due to lack of appropriate time series observations, then systematic surveys specifically targeting this period range could reveal a substantial population providing statistical samples for studying binary evolution, mass transfer physics, and gravitational radiation. Ground-based facilities contributed follow-up observations using rapid photometry instruments capable of time resolution better than 1 second. These observations confirmed the 37-second period and extended phase coverage to times when Webb observations couldn't be scheduled. The combination of space-based infrared data from Webb and ground-based optical data provides comprehensive characterization unavailable from either facility alone. Understanding what Webb detected requires examining theoretical frameworks explaining how stellar systems can achieve 37-second orbital periods and what physical processes create the observed variability. Compact binary star systems form when molecular cloud fragmentation or disk instabilities during star formation create two gravitationally bound objects orbiting their common center of mass. The initial orbital separations range from fractions of an astronomical unit to thousands of astronomical units depending on formation mechanism and environmental conditions. Most binaries form with separations large enough that both stars evolve independently without significant interaction beyond gravitational attraction. Closed binaries with separations less than roughly 10 astronomical units experience tidal interactions and possible mass transfer during stellar evolution. As stars evolve off the main sequence and expand into giant phases, their radii can increase by factors of 10 to several hundred. A star that formed with radius 1 solar radius might expand to 100 or more solar radii during red giant evolution, potentially engulfing a companion that orbits within this expanded envelope. Common envelope evolution occurs when one binary component expands to giant dimensions while the companion orbits within the expanded envelope. Friction between the companion and the giant's envelope causes the companion to spiral inward while transferring orbital energy to the envelope. This energy input can eject the envelope entirely, leaving behind the giant's core, now white dwarf, in a much closer orbit with the companion than before envelope ejection. The process can repeat if the companion also evolves into a giant and engulfs the white dwarf in a second common envelope phase. The outcome produces a double white dwarf binary with orbital separation determined by how much orbital energy was required to eject both envelopes. Theoretical models predict that common envelope evolution can produce double white dwarf binaries with periods ranging from hours to days depending on initial masses and separations. However, producing periods as short as 37 seconds through common envelope evolution alone appears challenging. The orbital energy available from in-spiral might not suffice to eject the envelope while leaving the cores at such extreme proximity. Additional mechanisms must operate to shrink orbits from the hours to days range achievable through common envelope to the seconds to minutes range observed in ultra-short period systems. Gravitational radiation provides the additional mechanism required. According to general relativity, accelerating masses emit gravitational waves carrying away energy and angular momentum. For binary systems, this gravitational radiation causes orbits to decay gradually, with decay rate increasing dramatically as orbital separation decreases. The orbital energy loss rate from gravitational radiation scales as the inverse fifth power of separation, meaning that cutting separation in half increases energy loss rate by factor 32. Double white dwarf binaries formed through common envelope with periods around a few hours experience gravitational radiation-driven orbital decay that gradually shrinks their orbits over billions of years. As separation decreases, decay accelerates, eventually bringing the system to periods of minutes and ultimately seconds. The time required to evolve from hour-long to minute-long periods can reach billions of years, comparable to or exceeding the age of the galaxy. Systems observed with periods around 37 seconds have likely been decaying for billions of years since their formation as our period binaries shortly after common envelope evolution. The current 37-second period represents a snapshot of ongoing evolution that will continue shrinking the orbit until one white dwarf begins transferring mass to its companion, or until the two white dwarfs eventually merge completely. The orbital separation corresponding to 37-second period depends on total system mass through Kepler's third law. For two white dwarfs each containing 0.6 solar masses, giving total mass 1.2 solar masses, the orbital separation calculates to approximately 170,000 kilometers. This separation barely exceeds the sum of two typical white dwarf radii around 5,000 to 10,000 kilometers each, placing the system on the verge of contact or mass transfer. White dwarf radii depend on mass through the mass-radius relationship for degenerate objects, where electron degeneracy pressure supports the star against gravitational collapse. More massive white dwarfs possess smaller radii because higher gravity compresses the degenerate electron gas to higher densities. A 0.6 solar mass white dwarf has radius approximately 8,000 kilometers, while 1.0 solar mass white dwarf shrinks to roughly 5,000 kilometers. The Roche lobe defines the critical equipotential surface within which material remains gravitationally bound to one binary component rather than the other. For each star in a binary, the Roche lobe radius depends on orbital separation and mass ratio. When a star's physical radius equals its Roche lobe radius, material at the stellar surface becomes gravitationally inbound and can flow to the companion through the inner Lagrange point where gravitat Idle forces balance. For the 37-second system with separation around 170,000 kilometers and comparable component masses, the Roslobe radii reach approximately 50,000 to 60,000 kilometers for each white dwarf. Typical white dwarf radii of 5,000 to 8,000 kilometers remain far below Roslobe radii, meaning that normal white dwarfs in such a system would not fill their Roslobes and no mass transfer would occur. However, one component might be a bloated low-mass white dwarf or a helium star that hasn't yet completed its evolution to a compact configuration. Low-mass white dwarfs with masses below approximately 0.3 solar masses possess larger radii than typical carbon-oxygen white dwarfs, potentially reaching 20,000 to 40,000 kilometers. Such an object in the 37-second system might approach or exceed its Roslobe radius, initiating mass transfer. Mass transfer in ultra-compact binaries proceeds through different mechanisms than in longer period systems. The extreme proximity creates strong tidal effects that synchronize rotation with orbital motion and circularize orbits. Material overflowing the Roslobe possesses significant angular momentum and cannot fall directly onto the companion. Instead, it forms an accretion disk where viscous processes transport angular momentum outward while material spirals inward. Accretion disks around white dwarfs in ultra-short period binaries remain relatively cool compared to disks in systems containing neutron stars or black holes. Because the lower surface gravity of white dwarfs means that material falling through the gravitational potential well gains less kinetic energy before impact. Disk temperatures reach 10,000 to 30,000 Kelvin rather than millions of degrees, creating emission primarily in optical and ultraviolet wavelengths rather than X-rays. The hot spot where the accretion stream from the donor star impacts the outer edge of the accretion disk can create localized regions significantly hotter than surrounding disk material. These hot spots rotating with the orbital period as the accretion stream location rotates around the disk create strong periodic variability. The rapid rise as the hot spot rotates into view and slower decline as it rotates away matches the pulse profile observed in the 37-second system. Alternatively, if one white dwarf possesses a strong magnetic field, material might not form a disk but instead follow magnetic field lines directly to the white dwarf's magnetic poles. This creates magnetic accretion similar to cataclysmic variables called polars and intermediate polars. Magnetic accretion produces different variability patterns depending on whether the white dwarf's rotation remains synchronized with orbital period or whether it rotates at a different rate. The mass transfer rate determines how much energy accretion releases and how bright the system appears. Transfer rates in ultra-short period systems typically range from 10 to 10 solar masses per year depending on donor star properties and evolutionary state. Higher transfer rates produce brighter systems but also drive angular momentum loss that can shrink orbits more rapidly than gravitational radiation alone. The evolutionary future of ultra-short period binaries depends on whether they merge or achieve stable mass transfer configurations. Systems that transfer mass faster than orbital decay can shrink might spiral together and merge, creating single objects with properties depending on component masses and compositions. Systems with lower transfer rates might reach equilibrium where mass transfer stabilizes, though such equilibria remain uncertain theoretically. Merged white dwarfs might explode as Type Ia supernovae if total mass exceeds the Chandrasekhar limit near 1 point for solar masses. Though recent models suggest that many mergers might not produce thermonuclear explosions. Alternatively, mergers create exotic remnant objects including single massive white dwarfs, helium stars, or even neutron stars depending on masses and compositions involved. Understanding the 37-second system requires determining component masses, radii, temperatures, and compositions through detailed modeling of light curves, spectra, and multi-wavelength emission. These measurements constrain evolutionary history and future fate while testing theoretical models of compact binary formation and evolution. Mass transfer physics material flows between binary components when one star fills its Roslobe and gas pressure pushes material beyond the gravitational equipotential surface, defining the boundary of gravitationally bound regions. The Roslobe overflow process initiates when stellar evolution increases stellar radius, when orbital decay shrinks the Roslobe. or when mass loss from stellar winds alters the mass ratio, changing Rho-slope geometry. The mass transfer rate depends on how far the donor star exceeds its Rho-slope radius and on the response of stellar structure to mass loss. Stars supported primarily by thermal pressure, like main sequence stars and giants, expand when they lose mass because removing mass from the surface reduces gravitational compression of underlying layers. This expansion can create unstable runaway mass transfer where the star expands faster than the Rho-slope, driving ever-increasing transfer rates. White dwarfs and other degenerate objects respond differently to mass loss because electron degeneracy pressure rather than thermal pressure provides support. Degeneracy pressure depends only on density, not temperature, making degenerate stars more stable against runaway mass transfer. However, low-mass white dwarfs and helium stars retain some thermal support, creating intermediate responses where mass transfer rates remain high but potentially stable. The stream of material leaving the donor star through the inner Lagrange point carries angular momentum that prevents it from falling directly onto the companion. Conservation of angular momentum requires that the stream follow trajectories curving around the receiving star. The stream's trajectory depends on the mass ratio between components and on the specific angular momentum the material possesses when leaving the donor. In most configurations, the material stream impacts the surrounding region rather than the stellar surface directly, creating a shock where the stream's kinetic energy converts to thermal energy. This impact creates the hot spot visible in optical and ultraviolet light as a bright region that rotates with the binary orbit. The hot spot's visibility varies with orbital phase depending on viewing geometry, creating the periodic variations observed. For sufficiently high angular momentum, the stream material cannot fall directly onto the star but instead settles into a rotating disk where viscous forces transport angular momentum outward while material spirals inward. Accretion disks form naturally in binary systems when the stream-specific angular momentum exceeds the value required for circular orbits at the stellar surface. Viscosity in accretion disks arises primarily from turbulence created by magnetic fields or hydrodynamic instabilities. The magnetorotational instability generates turbulence when weak magnetic fields couple to differentially rotating gas, creating fluctuations that transport angular momentum outward through correlated velocity and magnetic field perturbations. This process operates efficiently in ionized gas with temperatures exceeding roughly 1000 Kelvin. The viscous heating rate in accretion disks depends on viscosity strength, local density, and the velocity shear from differential rotation. Material rotating faster in inner regions and slower in outer regions experiences shearing motions that dissipate kinetic energy as heat through viscous friction. The heating rate per unit area increases towards smaller radii where orbital velocities increase and velocity gradients steepen. Temperature distributions in accretion disks follow from balancing viscous heating against radiative cooling. The disk radiates as an annular blackbody with temperature depending on radius, viscosity parameters, and mass transfer rate. For white dwarf accretion disks with typical parameters, temperatures range from 3000 Kelvin in outer regions to 30,000 Kelvin or more near the white dwarf surface. The spectrum emerging from an accretion disk includes contributions from all ANLI at different temperatures, creating a composite spectrum broader than a single temperature blackbody. The integrated spectrum shows emission from optical through ultraviolet wavelengths with strength depending on total accretion luminosity for the 37-second system. The observed infrared through optical emission suggests disk temperatures consistent with white dwarf accretion at moderate transfer rates. Disk instabilities can create additional variability. Beyond orbital modulation, the dwarf nova instability, driven by hydrogen ionization changing disk opacity and viscosity, creates outbursts where disk temperature and luminosity increase dramatically over timescales of days to weeks before declining back to quiescence over similar timescales. Whether ultra-short period systems like the 37-second binary experience such instabilities depends on mass transfer rate and disk properties. Magnetic fields threading the accretion disk or possessed by the accreting white dwarf modify the accretion flow geometry and create different variability patterns. Weakly magnetic white dwarfs might truncate the inner disk at radii where magnetic pressure exceeds gas pressure, creating boundary layers where disk material transitions to magnetic flow along field lines. Strongly magnetic white dwarfs prevent disk formation entirely, forcing material to follow magnetic field lines from the accretion stream directly to magnetic poles. Polars, the strongly magnetic case, show variability driven by viewing geometry modulating the visibility of magnetic accretion spots at white dwarf poles. The accretion spots emit cyclotron radiation from electrons spiraling in strong magnetic fields, creating highly polarized emission with characteristic spectrum. The spots appear and disappear as white dwarf rotation carries them in and out of view, creating periodic variations at the white dwarf spin period. Intermediate polars possess weaker magnetic fields allowing disk formation but still channeling inner disk material along field lines. These systems show variability at both orbital period from geometric modulation and spin period from rotating magnetic spots. The interplay between these periods creates beat frequencies and complex light curves requiring careful analysis to disentangle different periodicity sources. For the 37-second system, the observations suggest non-magnetic or weakly magnetic accretion where orbital period dominates. Variability, the absence of strong cyclotron features in optical spectra, argues against strong magnetic fields. The variability amplitude increasing toward longer wavelengths suggests that cooler emission components, possibly the donor star or outer disk regions, contribute substantially to infrared flux and modulate with orbital period. The donor star, illuminated by the hot accretion disk or accreting white dwarf, shows reflection effects where radiation heats the facing hemisphere to temperatures higher than the star's intrinsic temperature. The heated hemisphere appears brighter than the unheated hemisphere, creating once-per-orbit variability as the heated region rotates in and out of view. This reflection effect could contribute to the observed infrared variability. Mass transfer drives orbital evolution through angular momentum changes. When mass flows from the more massive to less massive component, the orbit shrinks. When mass flows from less massive to more massive component, the orbit expands. The specific outcome depends on how transferred mass affects orbital angular momentum and on whether mass leaving the system carries away angular momentum through winds or outflows. For double white dwarf systems, the donor typically has lower mass than the accretor because more massive stars evolved first and became white dwarfs earlier. Mass transfer from low mass to high mass component drives orbital expansion, potentially stabilizing systems against runaway mass transfer. However, gravitational radiation simultaneously drives orbital decay, creating competition between processes that expand and shrink orbits. The balance between mass transfer-driven expansion and gravitational radiation-driven contraction determines whether ultra-short period systems maintain stable periods or continue evolving. Systems with low mass transfer rates experience net orbital decay as gravitational radiation dominates. Systems with higher transfer rates might achieve equilibrium or even expand temporarily before decay resumes. Understanding mass transfer physics in the 37-second system requires measuring the transfer rate through luminosity observations, determining donor properties through spectroscopy, and tracking orbital period changes over years to decades to observe whether the system decays, remains stable, or expands. Gravitational waves. Einstein's general theory of relativity predicts that accelerating masses create ripples in spacetime geometry that propagate outward at light speed, carrying energy and angular momentum away from the source. These gravitational waves remain undetected for a century after Einstein's prediction until the Laser Interferometer Gravitational Wave Observatory achieved the first direct detection in September 2015 by observing spacetime ripples from merging black holes 1.3 billion light-years away. Gravitational wave emission from binary systems follows from the quadrupole formula relating radiated power to the system's time-varying mass quadrupole moment. For circular orbits, the quadrupole moment oscillates with twice the orbital frequency, creating gravitational waves at twice the orbital frequency. The power radiated scales as the sixth power of orbital frequency and the square of the reduced mass, making close, massive binaries the strongest sources. The 37-second orbital period corresponds to gravitational wave frequency 0.04 Hz, far below the 10 to several thousand Hz frequency range accessible to ground-based detectors like LIGO and Virgo. Ground-based interferometers cannot observe frequencies below roughly 10 Hz because seismic noise and gravity gradient fluctuations from nearby mass motions create overwhelming backgrounds at lower frequencies. Space-based gravitational wave detectors operating above Earth's atmosphere avoid seismic noise and can access frequencies from 0.001 Hz to 1 Hz. Exactly the range where ultra-short period binaries emit. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will observe gravitational waves from compact binaries with periods from seconds to hours, including systems like the 37-second binary discovered by Webb. LISA consists of 3 spacecraft forming an equilateral triangle with arm lengths up to 0.5 million kilometers, nearly 7 times the Earth-Moon distance. Laser beams transmitted between spacecraft monitor the arm lengths with picometer precision, detecting changes caused by passing gravitational waves that alternately compress and stretch space. The configuration allows simultaneous measurement in multiple directions, enabling skylocalization of gravitational wave sources. For the 37-second system at distance 1,400 light-years with estimated component masses around 0.6 solar masses each, the gravitational wave strain amplitude reaching Earth calculates to approximately 10. This means the fractional length change in LISAS to 0.5 million kilometer arms would reach about to 0.5 femtometers, roughly 100,000th the size of a proton. Despite this infinitesimal signal, LISAS sensitivity reaches approximately 10 at frequencies near 0.05 Hz, making the 37-second system detectable. Detection requires integrating signal over months to years to build sufficient signal-to-noise ratio. Gravitational waves from persistent sources like compact binaries remain in band for the entire mission lifetime, allowing coherent integration that improves sensitivity proportional to the square root of observation time. A system marginal for detection in 1 month becomes highly significant after 1 year of integration. The gravitational wave signal from binary systems contains information about component masses, orbital period, period derivative, distance, and binary inclination. Measuring the wave frequency determines orbital period directly. The frequency evolution over time reveals period derivative, which for circular orbits relates directly to orbital decay rate from gravitational radiation. Signal amplitude depends on masses, distance, and inclination, creating parameter degeneracies that require combining gravitational wave data with electromagnetic observations. For the 37-second system, electromagnetic observations from Webb and other telescopes provide independent constraints on masses, period, and distance. Combining these electromagnetic measurements with LISA gravitational wave detections breaks degeneracies and enables precision tests of general relativity. Any discrepancy between observed orbital decay rate and theoretical predictions would indicate physics beyond general relativity or unexpected contributions from tidal effects or mass transfer. The orbital decay time scale, the time required for period to change substantially, depends on masses, separation, and current period through the gravitational radiation formula. For 0.6 solar mass white dwarfs orbiting with 37-second period, calculations predict period derivative around -1, 2 times 10, meaning the period decreases by approximately 12 nanoseconds per second or roughly 400 milliseconds per year. Over 1 million years, the period would decrease by approximately 10%, shrinking from 37 seconds to about 33 seconds. Over 10 million years, the period drops to roughly 20 seconds. Eventually, continued decay brings the system to periods below 10 seconds where tidal effects become extreme and mass transfer likely initiates if it hasn't already. The ultimate fate involves merger on timescales of tens to hundreds of millions of years depending on exact masses and whether mass transfer alters evolution. The gravitational wave frequency evolution creates a characteristic chirp signal where frequency increases gradually as the orbit decays. LISA observing for several years will measure the frequency derivative directly through the changing gravitational wave pitch. This measurement provides the most direct test of general relativity's prediction for gravitational radiation from compact binaries, complementing previous tests using pulsar timing. Binary pulsars, systems containing pulsars orbiting companion stars or compact objects, enabled the first indirect detection of gravitational waves through measurements of orbital decay. The Hulse-Taylor binary pulsar discovered in 1970 showed orbital decay precisely matching general relativity predictions, confirming that gravitational radiation carries away orbital energy as Einstein's theory requires. This discovery earned the 1993 Nobel Prize in Physics. The double pulsar system discovered in 2003 provides even better tests because both neutron stars emit radio pulses, allowing measurement of both orbital motions independently. The orbital decay matches general relativity predictions to better than 0.1%. The most precise test available, however, pulsar timing provides indirect detection, measuring gravitational wave effects rather than the waves themselves. LISA's direct detection of gravitational waves from ultra-short period binaries will complement pulsar timing tests by observing waveforms directly rather than inferring emission from orbital decay. The waveform phase evolution encodes information about masses, spins, and potentially even tidal deformations if components possess significant tidal bulges. Measuring these effects tests general relativity in regimes where strong gravitational fields and high velocities create substantial spacetime curvature. The population of ultra-short period binaries observable by LISA includes thousands to tens of thousands of systems across the galaxy. The most numerous sources will be double white dwarf binaries with periods from minutes to hours. The shortest period systems with periods below 1 minute will stand out as individually resolvable sources, while longer period systems create a confusion-limited background of overlapping signals. The 37-second system, among the shortest period binaries known, will be easily resolvable and likely among the loudest sources in LISA's band. Its electromagnetic brightness allowing detailed characterization through optical, infrared, and potentially X-ray observations makes it particularly valuable for combining electromagnetic and gravitational wave data. Such multi-messenger observations enable measurements impossible from either data type alone. Measuring gravitational wave polarization, the orientation of spacetime stretching and squeezing, provides information about binary inclination and distance. Gravitational waves possess depolarization states corresponding to stretching along different axes perpendicular to propagation direction. The relative amplitude of these polarizations depends on viewing angle, allowing inference of binary orientation in space. For the 37-second system, combining polarization measurements with radial velocity amplitudes from spectroscopy determines absolute masses rather than just mass ratios. Spectroscopy measures the quantity m sin I, where m represents mass and I represents orbital inclination. Gravitational waves measure both m and I independently, allowing solution for both quantities separately. This mass determination provides crucial constraints for understanding stellar evolution and white dwarf physics. The eventual merger of ultra-short period binaries like the 37-second system will create transient gravitational wave signals as orbital frequency sweeps upward through LISA's band. Before the components coalesce, merger signals contain information about final moments of inspiral, the merger itself, and the ring down as the merged remnant settles into equilibrium. These signals test general relativity in the highly dynamical regime where velocities approach light speed. Understanding gravitational radiation from the 37-second system connects electromagnetic observations of this individual object to the broader population of compact binaries LISA will observe, providing crucial benchmarks for gravitational wave astronomy and tests of fundamental physics. Observational techniques. Detecting and characterizing ultra-short period variable stars requires specialized observational techniques optimized for measuring brightness changes on timescales of seconds to minutes. Traditional astronomical observation strategies designed for studying steady sources or slow variables prove inadequate when variability timescales drop below typical exposure times. New approaches combining rapid photometry, high-speed spectroscopy, and coordinated multi-wavelength campaigns enable comprehensive study of these extreme systems. High-speed photometry employs detectors capable of reading out measurements every second or faster while maintaining sufficient sensitivity for detecting faint sources. Charge-coupled devices traditionally used for astronomical imaging require seconds to minutes for readout, limiting time resolution. Modern detectors including electron-multiplying CCDs and avalanche photodiode arrays achieve readout rates exceeding 1,000 frames per second while maintaining quantum efficiency above 50%, enabling detection of variations on millisecond timescales. For the 37-second system, photometry with cadence around 1 second provides approximately 35 measurements per cycle, sufficient for characterizing pulse profile shape and measuring pulse arrival times to precision. Better than 1 second. The photometric precision achievable depends on source brightness, detector quantum efficiency, and sky background levels. For moderately bright sources like the 37-second system, single measurements reach precision around 1% to 5%, while averaging over multiple cycles improves precision proportionally to the square root of cycle number. Filter selection determines which wavelength ranges contribute to photometric measurements. Broadband filters passing light across ranges spanning hundreds of nanometers maximize photon collection and enable detection of fainter sources. Narrowband filters isolating specific wavelength regions reduce background but require longer exposures to achieve equivalent signal-to-noise ratios. 4. Time domain studies. Broadband filters generally provide better results and less specific spectral features require isolation. Webb's infrared observations used filters spanning 1 to 5 microns in NIRCam and 5 to 28 microns in MIRI, providing wavelength coverage unavailable from ground-based facilities where atmospheric absorption blocks most infrared light. The combination of space-based infrared data from Webb and ground-based optical data from facilities using high-speed photometry creates comprehensive spectral energy distributions showing how emission varies with both wavelength and time. Time series spectroscopy obtains complete spectra repeatedly at cadences matching variability timescales, enabling measurement of how spectral features change during variability cycles. Traditional spectroscopy integrates light over minutes to hours to achieve sufficient signal-to-noise for detecting faint spectral features. Rapid spectroscopy sacrifices spectral resolution or signal-to-noise to achieve faster cadence, trading detailed feature characterization for temporal information. For the 37-second system, spectroscopy with cadence around 10 to 20 seconds provides 3 to 7 spectra per orbital cycle, sufficient for measuring radial velocity variations and tracking how emission line strengths change with orbital phase. The spectral resolution required depends on stellar velocity amplitudes and line widths. Resolving power around 1000 to 3000 suffices for measuring radial velocities to precision around 10 km per second. Adequate for compact binaries with velocity amplitudes around 100 to 300 km per second. Doppler tomography combines time series spectroscopy with orbital phase information to reconstruct two-dimensional velocity maps showing emission distribution as functions of both velocity components perpendicular and parallel to the line of sight. This technique reveals structures like accretion disks, gas streams, and hotspots by mapping where emission rises in velocity space. The maps show spiraling disk gas, ballistic stream trajectories, and localized hotspot emission as distinct features at specific velocity coordinates. Applying Doppler tomography to the 37-second system requires obtaining complete spectroscopic time series covering at least one full orbital cycle with sufficient phase resolution to resolve structural features. Observations spanning multiple cycles allow averaging that improves map signal-to-noise while revealing whether structures remain stable or evolve over time. The resulting velocity maps constrain disk radius, stream trajectory, hotspot location, and other geometric properties difficult to measure through direct imaging. Polarimetry measures how light's electric field vector orientation changes with time, revealing information about scattering geometry, magnetic fields, and emission mechanisms. Polarization arises from scattering in non-spherical geometries, from synchrotron or cyclotron emission in magnetic fields, and from several other physical processes. Measuring polarization as functions of wavelength, time, and orbital phase constrains emission mechanisms and geometric configurations. For accreting binary systems, Polarization can reveal whether accretion proceeds through disks creating scattered light polarization or through magnetic funneling creating cyclotron emission polarizati. On. The time dependence shows whether polarization remains constant or modulates with orbital or spin periods. Wavelength dependence distinguishes mechanisms since different processes create characteristic polarization spectra. Eclipse mapping exploits the geometric occultation occurring when one binary component passes in front of the other to create spatial maps of emission regions. As the eclipsing object crosses the emitting region, different portions become occulted at different times, creating time-dependent brightness changes encoding spatial information. Inverting these light curves through maximum entropy or other reconstruction techniques produces two-dimensional maps showing emission distribution projected onto the sky. The 37-second system's orientation determines whether eclipses occur. If orbital inclination reaches approximately 80 to 90 degrees, implying nearly edge-on viewing. Eclipses will occur once per orbit as each component occults the other. The eclipse depths and durations constrain component radii and orbital separation. The detailed eclipse light curve shapes reveal whether emission regions possess structure or remain uniform. Multi-wavelength campaigns coordinating simultaneous observations across the electromagnetic spectrum from radio through X-rays provide comprehensive characterization impossible from single wavelength data. Different emission mechanisms dominate at different wavelengths, making multi-wavelength coverage crucial for understanding which physical processes operate. Radio observations trace synchrotron emission and thermal bremsstrahlung from ionized gas. Infrared observations detect coal components and dust. Optical and ultraviolet light reveals hot accretion regions. X-rays trace the hottest gas and hard radiation from magnetic reconnection or shocks. For the 37-second system, coordinated observations using Webb for infrared, Hubble for optical and ultraviolet, and Chandra for X-rays map emission from cool donor star through intermediate temperature disk 2. Hot accretion spots and potential X-ray emitting regions. The phase relationships between variability at different wavelengths constrain emission geometry and reveal whether different components vary in phase or with phase offsets indicating spatial separation. Long-term monitoring tracking brightness and period over months to years enables measurement of secular changes impossible to detect in short observational baselines. Period derivatives from orbital decay require measuring periods to microsecond precision across time baselines of months to years to detect changes at 10 level. Brightness evolution might reveal changes in mass transfer rate or accretion disk state occurring over timescales longer than individual observations. Amateur astronomers equipped with charge-coupled device cameras and accurate timing systems contribute valuable long-term monitoring that professional facilities cannot provide given oversubscribed telescope time. Networks of amateur observers coordinate observations maintaining nearly continuous coverage of bright variables, detecting outbursts, measuring eclipse dimmings, and contributing timing measurements for orbital decay studies. The 37-second system's moderate brightness makes it accessible to amateur telescopes, enabling community participation in scientific research. Archival data mining searches through existing astronomical survey databases for previously unrecognized variability. Large sky surveys like the Zwicky Transient Facility, ATLAS, and PanSTARRS observe millions of sources repeatedly over months to years, accumulating time series data that can be analyzed retrospectively to identify periodic variables. Automated pipelines search for periodicities across timescale ranges from minutes to years, discovering variables missed by targeted searches. The discovery of the 37-second system in Webb archival data demonstrated the value of systematically searching infrared time series observations. Similar searches through optical survey data might reveal additional ultra-short period systems. Building statistical samples for population studies. The growing volume of time domain astronomical data promises continued discovery of rare or extreme variables as search techniques improve and databases expand. Understanding observational techniques required for studying ultra-short period systems highlights the specialized approaches needed to detect and characterize objects varying on timescales challenging even for modern instrumentation. Theoretical models explaining the 37-second periodic system requires theoretical models connecting observed properties to underlying physical parameters and evolutionary histories. Models must predict the period stability, variability, amplitude, wavelength-dependent emission, and spectroscopic characteristics while remaining consistent with binary evolution theory and observations of similar systems. Multiple model approaches attempt to reproduce observations, each making different assumptions about system parameters and dominant physical processes. Binary evolution models trace stellar evolution from zero-age main sequence through giant phases, common envelope evolution, white dwarf formation, and eventual orbital decay to ultra-short periods. These calculations solve stellar structure equations following how stars respond to nuclear burning, mass loss, and binary interactions across billions of years. The models predict which initial binary configurations produce ultra-short period systems and on what timescales. Modeling binary evolution requires specifying initial conditions including component masses, orbital period, eccentricity, metallicity, and rotational velocities. Evolutionary codes integrate stellar structure equations forward in time while accounting for nuclear reactions, convective mixing, mass loss through winds, tidal interactions, and mass transfer when stars fill Rosse lobes. Common envelope phases receive special treatment because the physics governing envelope ejection remains poorly understood. For the 37-second system, binary evolution models explore which initial conditions could produce the current configuration. The presence of at least one white dwarf indicates that at least one component completed main sequence and giant branch evolution. The extremely short period requires substantial orbital shrinkage from initial separations, likely through common envelope evolution followed by billions of years of gravitational radiation-driven decay. The models predict that initial systems might have contained two stars with masses around 2 for solar masses each orbiting with periods of days to months. The more massive star evolved first, expanding to red giant dimensions and engulfing the companion in common envelope. Friction ejected the envelope, leaving a white dwarf orbiting the still evolving companion with period perhaps tens of hours. The second star eventually evolved, potentially undergoing its own common envelope phase or simply expanding enough to transfer mass to the white dwarf. This second evolution further shrank the orbit or altered the mass ratio. Following these active evolution phases, gravitational radiation gradually decreased the period over billions of years, eventually reaching the current 37-second value. Accretion disk models calculate disk structure and emission by solving equations for mass conservation, angular momentum transport, and energy balance throughout the disk. These models predict temperature, density, and velocity distributions as functions of radius. The solutions depend on mass transfer rate, viscosity parameters, and boundary conditions at the white dwarf surface and outer disk edge. For typical viscosity parameters and mass transfer rates around 10 to 10 solar masses per year. Disk models predict temperatures ranging from several thousand Kelvin in outer regions to tens of thousands Kelvin near the white dwarf surface. The disk radiates as a composite blackbody with spectrums showing emission from optical through ultraviolet wavelengths. The total luminosity depends primarily on mass transfer rate and white dwarf mass. The hot spot where the accretion stream impacts the outer disk edge receives special treatment in models. The stream velocity at impact reaches several hundred kilometers per second, creating shocks that dissipate kinetic energy as heat. The shocked region might reach temperatures of 30,000 to 100,000 Kelvin, substantially hotter than surrounding disk material. This temperature difference creates the bright spot visible as modulated emission. Light curve models calculate expected brightness variations by integrating emission from all visible components including white dwarfs, accretion disk, hotspot, and donor star, accounting for geometric viewing effects, eclipses, and irradiation heating. The models predict how brightness varies with orbital phase for different system parameters and viewing geometries. For the 37-second system, light curve models that include a donor star, accretion disk, and bright hotspot reproduce the observed pulse profile showing rapid rise and slower decline. The rise occurs as the hotspot rotates into view, while decline reflects the spot rotating behind the accretor and additional contributions from radiation-heated regions on the donor star becoming visible and then disappearing. Spectroscopic models predict emission line profiles by calculating line formation in disk atmosphere, spot region, and stellar photospheres while accounting for Doppler shifts from orbital motion and disk rotation. The models show how line strength and profile shape vary with orbital phase depending on emission region geometry and kinematics. Emission lines from highly ionized species like helium and heavier elements arise primarily in hot regions including the accretion spot and possibly a boundary layer where disk material settles onto the white dwarf surface. These lines show double-peaked profiles characteristic of rotating disk emission plus single-peak components from localized spots. The line velocities measure orbital motion and disk rotation speeds, constraining masses and disk radius. Population synthesis models calculate the expected number and properties of ultra-short period binaries by evolving large numbers of initial binaries through complete evolutionary sequences and determining which produce systems matching observational selection criteria. These models predict detection rates for surveys with specified sensitivity and sky coverage. Current population synthesis calculations predict that ultra-short period binaries with periods below 1 minute should number in the thousands to tens of thousands across the galaxy. However, most remain undiscovered because surveys have lacked the time resolution and sky coverage to detect them efficiently. Webb's discovery of the 37-second system suggests that systematic infrared time domain surveys might reveal substantial populations. The models also predict period distributions, mass distributions, and evolutionary states of ultra-short period systems. Most should contain double white dwarf binaries with masses around 0.2 to 0.8 solar masses each. Reflecting the most common stellar evolution outcomes, a smaller fraction might contain white dwarfs paired with helium stars or low-mass main sequence stars that haven't yet evolved to white dwarfs. Gravitational wave models calculate expected waveforms and detection prospects for space-based detectors like LISA. The models predict strain amplitudes, frequency evolution, and parameter estimation precision for binaries with specified masses, periods, and distances. These calculations show that LISA will detect thousands of galactic compact binaries, with the shortest period systems standing out as individually resolvable sources. For the 37-second system at 1,400 light-years with estimated component masses around 0.6 solar masses, models predict LISA detection with signal-to-noise ratio around 50 to 100 after several years of integration. This high significance will enable precision measurements of masses, period derivative, and binary orientation. The electromagnetic brightness allowing detailed optical and infrared characterization makes this system particularly valuable for multi-messenger astronomy combining gravitational wave and electromagnetic data. Merger models follow the final evolution as orbital decay brings white dwarfs into contact, and they coalesce into single objects. The merger outcomes depend sensitively on component masses, mass ratios, and compositions. Equal mass mergers of carbon-oxygen white dwarfs might produce massive white dwarfs, while unequal mass mergers could trigger runaway thermonuclear burning creating type Ia supernovae or unusual transient events. Recent hydrodynamic simulations suggest that many white dwarf mergers do not explode as supernovae but instead create single massive white dwarfs or exotic helium stars. The conditions determining explosion versus quiescent merger remain uncertain, representing one of the key questions about type Ia supernova progenitors. Observations of ultra-short period systems approaching merger provide crucial constraints on progenitor properties. Comparing theoretical predictions to observations of the 37-second system and similar objects tests models and reveals where current understanding remains incomplete. Discrepancies between predicted and observed properties indicate missing physics or incorrect assumptions, driving model improvements and advancing understanding of compact binary evolution. Similar systems. The 37-second system joins a small but growing collection of ultra-short period binaries discovered over the past decades through dedicated searches and serendipitous detections. Each system reveals unique characteristics while sharing common features indicating related evolutionary origins. Comparing these objects provides statistical constraints on formation, channels, evolutionary timescales, and physical processes operating in extreme compact binaries. Canum venaticarum variables represent one class of ultra-short period binaries showing hydrogen-deficient spectra and periods ranging from approximately 5 minutes to 65 minutes. These systems contain white dwarfs accreting helium-rich material from helium white dwarf or helium star donors. The absence of hydrogen in their spectra distinguishes them from typical cataclysmic variables and indicates that donors never possessed hydrogen-rich envelopes or lost them through previous evolution. The shortest period AMCVN system, HM Concrete, orbits with period approximately 321 seconds or 5.4 minutes, making it the shortest confirmed orbital period for any binary star system before the 37-second discovery. HM Concrete shows variability at the orbital period and at a superhump period slightly longer than orbital period, created by disk precession. The system serves as a prototype for ultra-compact binaries and a verification source for LISA gravitational wave detection. RxJ0806, another ultra-short period system, shows 321-second X-ray pulses originally interpreted as rotation of a massive white dwarf but later understood as orbital period of a compact binary. The system contains two white dwarfs with total mass around 1 point to solar masses orbiting at separation approximately 90,000 kilometers. The X-ray emission arises from shocks where a weak accretion stream impacts the disk or white dwarf surface. V407 Vulpeculae represents a slightly longer period system at 569 seconds showing similar characteristics to shorter period objects. The system undergoes outbursts increasing brightness by several magnitudes over time scales of hours to days, possibly driven by thermal instabilities in the accretion disk similar to dwarf nova outbursts in longer period systems. The outburst mechanism in helium accreting systems differs from hydrogen accreting disks due to different ionization physics and opacity sources. ZTF-J1539 plus 5027 discovered in 2019 by the Zwicky Transient Facility shows a 6.91-minute orbital period, making it one of the shortest periods known. The system likely contains a white dwarf accreting from a brown dwarf or very low-mass star based on optical and ultraviolet observations constraining component temperatures and luminosities. The donor mass estimated around 0.05 solar masses places it near the hydrogen burning limit separating stars from brown dwarfs. Comparison between systems reveals correlations between period, mass transfer rate, and spectral characteristics. Shorter period systems generally show higher mass transfer rates because closer separation means that smaller radius changes suffice for Roche lobe overflow. Higher transfer rates produce brighter accretion disks and more prominent emission lines, however. The relationship shows substantial scatter indicating that donor properties and evolutionary states vary considerably among systems. The period distribution of known ultra-short period binaries shows a gap between roughly 40 seconds and 5 minutes with few confirmed systems. The 37-second discovery partially fills this gap, but substantial regions remain sparsely populated. This gap might reflect selection effects where systems in this period range remain difficult to detect with current survey strategies. Or it might indicate genuine rarity reflecting specific evolutionary pathways required to produce such systems. Theoretical predictions suggest that double white dwarf binaries should exist across the full period range from seconds to hours, with numbers increasing toward longer periods. The observed gap might result from mass transfer stabilizing at specific period ranges or from observational biases against detecting certain system types. Systematic searches specifically targeting the 40-second to 5-minute range could test whether the gap reflects real paucity or selection effects. Variability amplitudes show wide diversity among ultra-short period systems. Some objects show variations exceeding factor 5 between maximum and minimum brightness, while others vary by only 20% to 50%. The amplitude depends on viewing geometry, mass transfer rate, hotspot brightness, and contribution from steady emission components like donor stars or inner accretion disks. The 37-second system's factor 3 variability amplitude falls within typical ranges but toward the higher end, suggesting that the hot spot contributes substantially to total luminosity. Systems with lower amplitudes might have more face-on orientations, reducing eclipse depths and geometric modulation. Or they might have lower mass transfer rates, producing fainter hot spots relative to steady disk emission. Spectroscopic characteristics vary from pure helium emission in classical AMCVN stars to systems showing some hydrogen features, suggesting that donors retain hydrogen envelopes. The 37-second system spectrum showing both hydrogen and helium emission indicates either a donor with hydrogen-rich envelope or contamination from an additional component. Detailed abundance. Measurements distinguishing between these possibilities require high signal-to-noise spectroscopy. X-ray emission appears in some ultra-short period systems but not others, depending on accretion geometry and boundary layer physics. Systems with strong X-ray emission might possess boundary layers where disk material settles onto white dwarf surfaces, releasing gravitational potential energy as X-rays. Systems with weak or absent X-rays might have inefficient boundary layers or might accrete at rates too low to produce substantial X-ray luminosity. The 37-second system's faint X-ray emission detected by Chandra indicates that while hot gas exists, the X-ray luminosity remains modest compared to systems like RxJ0806. This suggests either lower mass transfer rate or less efficient conversion of accretion energy to X-rays. Further X-ray spectroscopy could determine plasma temperatures and abundances constraining accretion shock physics. Outburst behavior, where systems suddenly brighten by magnitudes before declining over days to weeks, occurs in some ultra-short period systems. These outbursts resemble dwarf nova eruptions in longer period cataclysmic variables and likely rise from thermal viscous instabilities in accretion disks. However, helium accreting disks show different instability conditions than hydrogen accreting disks, and the shortest period systems might remain stable, avoiding outbursts entirely. Whether the 37-second system undergoes outbursts remains unknown given the limited observational baseline. Long-term monitoring could detect outbursts if they occur or establish upper limits on outburst frequency and amplitude. The detection of even when outburst would provide crucial constraints on disk physics and mass transfer rate variations. Magnetic field strengths measured in some ultra-short period systems range from undetectably weak to several megagauss for strongly magnetic white dwarfs. Systems with strong fields channel accretion along magnetic field lines, creating polars, while weakly magnetic systems allow disk formation, creating disk-fed accretion. The magnetic field evolution in compact binaries remains poorly understood, with questions about field generation, decay, and possible amplification through accretion. The 37-second system shows no clear signatures of strong magnetic fields based on current spectroscopy, suggesting either weak or absent fields. However, fields below roughly 1 megagauss might escape detection in moderate resolution spectra. So high-resolution spectropolarimetry would be needed to confirm field absence or detect weaker fields. Gravitational wave detection prospects differ among systems depending on distance, mass, and period. Nearby systems with large masses and short periods produce the strongest gravitational wave signals, potentially detectable by least in days to weeks of integration. More distant or lower mass systems require months to years for confident detection. The 37-second system's moderate distance and estimated masses place it among systems LISA should detect relatively easily. Statistical studies of ultra-short period populations constrain binary evolution theory by testing predicted period distributions, mass distributions, and space densities. Current samples remain small with substantial observational biases, but future surveys will build larger samples, enabling more robust statistical tests. The discoveries expected from LISA will dramatically expand known populations by detecting thousands of systems through gravitational waves. Understanding how the 37-second system compares to similar objects contextualizes its properties and reveals whether it represents a typical example or an unusual outlier among ultra-compact binaries.